Hello? Did you get your exam back? Okay, your name?
Kate.
Okay. We'll just say that. Please? Here we go.
Thank you.
Okay. Thank you. All right. Let's do it. Stop it. We are? Okay. All right. Okay. Well, he has to work one more, actually 2 more days, right? So what happens with, like, are most people going to just stay in the dorm, or are they gonna go back home, or what's
I'm a sophomore, so I live on campus.
okay,
You live
Yeah,
on
I'm
campus?
going.
you're going to go home? Okay. So about maybe half and half, then.
Yeah, because I mean, it's like all of that.
I think like a very small percentage will stay here.
Okay.
And like if you live on campus, but I know like living off campus, I'm staying here. I'll go home for a week for the holiday, but I'll come here. I'll stay.
Did you get your list done? Okay, hang on, just stay there. I'll call. So like for spring semester, are they going to do sort of finals in person? Or?
Not really sure. They might just like see how it goes and then maybe give it to like the option of professors.
Right.
I think it'd be close to that. Okay. Deciding what to do.
Okay, because you're doing the same way we're doing, just kind of split the class.
I'm surprised more teachers haven't done that. Like this is my only class where we come in to take the test. My other math class, we do it online. He sends us the test, we send it back to grade school.
Oh, sorry, did you get the agenda?
No, sorry.
Okay, so, let's see, you're in?
Music.
Okay, John.
You're cute. Oh, really? You think you've got this something honestly. Kind of sweet there. Thank you.
Good.
I'm about to go there after this. I flew this one
So this is the only class that actually has in-person exam.
for me, please.
Yeah.
Oh,
Yeah. But I mean, I kind of prefer it, oddly enough. Because with that other math class, it's like, it's supposed to take an hour, but like it might take 8 hours. Because I go through every single problem,
yeah.
and we can use our notes, so I'm going through all of my notes. And it's 3,100
Yeah.
with Dr. Pollock, and he's a really good teacher. The class is really hard. So it's a lot harder to be in this class.
Oh, yeah. Yeah, so yeah, we'll have to do things, of course, online. I'm sort of just trying to decide about whether I make an open book or I just give you like one sheet to read or something like that. Probably should not. It might be just good to you like, wrote a sheet out and wrote it yourself. So, is it one?
You can follow. I've already used like $700. It's going pretty fast. And I've only had like 3 lessons. No, 3,500. You can fly. You got the 8. Did you set up your?
Okay, let's see how many people get me.
Highly recommend pressing. He's really cool. He's mine. Really? You paid? Two days from now. It's really easy. It's $1,000. Yeah. You should. It's fun.
Okay, so we should probably get started. Can people out there on Zoom hear me? Yes?
Yes.
Okay, thanks. All right, so today what we'll do is we'll go over the notion of orthogonal sets. So what we're going to do is we're going to actually look at sets where the vectors are orthogonal to one another. So let me make a standard definition. So definition, a set of vectors that's called U1, U2, up to UT inside of Rn is called orthogonal if and only if, well, we just want pairwise for them to be orthogonal. So ui dot uj is equal to 0 for I not equal to j. Okay, so an orthogonal set, the picture you should be thinking about is you have vectors which look kind of like that. Right, so each of them is mutually orthogonal to one another. So the dot product is actually equal to 0. So this would be U1, U2, and U3. Okay, so that's the picture you should be thinking about. All right, now the set is orthonormal if they'll have unit length 1. So a set of vectors U1 up to UT is orthonormal if and only if it is, first of all, orthogonal, and each vector is unit length 1. So, and the length of each vector is equal to 1. for all j. This is the for every symbol. Means for all. So maybe some people have seen it before. Okay. All right, so let me give you an example. So let x, let me just call it u1. So u1 is 1 minus 2, 1. And u2 is going to be equal to 0, 1, 2. And u3 is equal to minus 5, minus 2, 1. Okay. All right. So the question is this an orthonormal or orthogonal set? So first of all, let's see if it's an orthogonal set. So to check whether it's orthogonal or not, what do we have to do? Right, so we take the dot product between, like, pairs, right? So let's say I take u1 dot u2. So if I take the dot product of u1 and u2, is it 0 or not? Take a look. 0 plus minus 2 plus 2, right? So it's dot product is 0. So if I take u1 dot u3, is the dot product going to be 0? So then minus 5 plus 4 plus 1, which is 0. Okay, good. So what else do we have to check? Good. So u2 dot u3. Let's check that real quick. That's again minus 2 plus 2, right? And that's 0. All right. So with these calculations, u1, u2, and u3 are orthogonal. Okay. Is this set orthonormal or not?
No.
No. Okay, so it's not orthonormal because, well, I could just take the length of u1, right? And that's the square root of 1 squared plus minus 2 squared plus 1 squared, which is the square root of 6. Okay, which is not 1. So it's not orthonormal. So how do I make this set orthonormal?
Divide by the magnitude.
Good. So now to make this set orthonormal, we can divide by the lengths. All right, so I get, so if you do this as 1 over the square root of 6 times u1, and the second one is, okay, the square root of 1 squared plus 2 squared, that's the square root of 5, right? So that's 1 over the square root of 5 times u2. And the third one is, well, yeah, thank you. Okay, good. Square root of 30, u3. Okay, so this is an orthonormal set. Okay. All right. Now, why is it nice to have an orthonormal set? Well, an orthonormal set is great in terms of taking inner products. Because if I take an inner product of one element in the orthonormal set with another element, then it only lights up when I actually have the same element involved. So this allows us to prove the following. So here's the theorem. Okay, so 1. So let u1 U2 up to UT be an orthogonal set. Okay. Then the set is linearly independent. Okay. 2. This follows from 1. So if, call it script B, U1 up to UT is an orthogonal set, then script B is a basis for the span. Okay, so this is sort of easy to see because first of all, by 1 we know it's linearly independent, and then if I take something in the span, it's a linear combination of U1 up to UT. Okay, so these vectors actually span the set. Okay. All right. So finally, let y be equal to C1 U1 plus CT UT. Okay, so the u's are in this orthogonal set. So then the coefficients have a very special form. So then Cj is equal to y dot uj over uj dot uj. Okay, so you can actually write the coefficients in terms of just dot products. This is for all j. Now, as we know, if we want to write something as a linear combination of some vectors, we have to use Gaussian elimination. But when you have an orthogonal set, you don't need to use Gaussian elimination at all. You can just take inner products. So that's why it's kind of nuts. So let me just state that. So normally, one would use Gaussian elimination to find Cj. But when the set U1 up to UT is orthogonal, one can find Cj by just taking dot products. You know, it's much easier than trying to use Gaussian elimination. Okay, any questions on this? Okay, so let me show you why this is true. So let me give you a proof. Okay, so first of all, sort of 2 follows from 1. Okay, so linear independence follows from 1, and spanning just follows because the span of the set is just the span, right? Okay, so let's do 1. So let's show that they're linearly independent. So you take C1 U1 plus C2 U2 plus CT UT being 0. Okay, so this is a common trait. So what we want to do is we're going to show that all the C's are equal to 0, right? The CI's are equal to 0. So what we can do is we can take the dot product of UJ with both sides. So when I take, so let J be equal to 1, 2, up to 2, okay? So if I take UJ dot C1 U1 plus CT UT, that's going to be equal to UJ dot 0, which is 0 scale, okay? But notice that the UJ dot with anything other than UJ is equal to 0. So the left-hand side is just going to be CJ uj dot uj. Okay? And now we know that uj is not equal to 0. The dot product's not 0 because uj is not equal to 0. So this implies that cj has to be equal to 0. And this happens for all j. So hence, the set u1 up to ut is linearly independent by definition. So we start with a linear combination which is equal to 0. We're going to show all the coefficients are equal to 0. Okay? So now 3 sort of follows in the same vein as the proof of 1. So suppose that y is equal to c1 u1 plus c2 u2 plus ct ut. Okay? And so now I can just take the dot product on both sides with uj. So if I take y dot uj on that side, well, again, uj times dot anything else other than uj is going to be 0. So I just get cj uj dot uj, just like before. And then I just move the uj dot uj to the other side. So hence, the coefficient is equal to y dot uj over uj dot uj. And this happens for all j. Okay. All right, any questions on this? Okay. All right, so let's put down the old tombstone here, saying that we've killed the proof. All right, so now let's make a definition. So let W equals the span of U1, U2 up to UT, where this is an orthogonal, where U1, U2 up to UT is an orthonormal basis. Okay, so basically I just need them to be orthogonal and then for them to have unilike 1. Actually, I didn't state that quite correctly here. Let me state it this way. So let's assume that this is an orthonormal set. Okay. So then from the previous theorem, we know that this U1, U2 up to UT is an orthonormal basis for W. Okay. All right, so whenever you have an orthonormal set, you have an orthonormal basis for the span of that set. That's all I'm saying. All right. Okay, so a few more things. So I don't know how much we'll be doing this, but let me just give you the definition. So an n by n matrix is called orthogonal. This is a little bit confusing because for it to be orthogonal, you have to have the rows or columns to be an orthonormal set. So if and only if I take a matrix, I have to call it U. So U times U transpose is the identity, and it's equal to U transpose times U. Okay, so an m by n matrix U is orthogonal if you take U times U transpose, you get the identity. So in other words, the transpose of the matrix is actually equal to the identity. So i.e. U transpose is equal to the identity. Okay. All right, so here's a theorem that you could prove about orthogonal matrices. So first statement, any orthogonal matrix has orthonormal columns and rows. Okay, so if I take the columns of this matrix, U transpose is the identity, and U transpose U is the identity, then if I take the columns, it forms an orthonormal set. Okay. Actually, an orthonormal basis for Rn. And then the same with the rows. So whenever you have a, so I guess let me say, let U be orthogonal. Okay, so whenever you have an orthogonal matrix, it also preserves length. So if I take the length of U times X, this is always equal to the length of X. It doesn't change the length of vectors. 3, if I take U times X and U times Y, this is U times U dot XY. All right. And finally, if I take UX times U dot Y, that's equal to 0 if and only if X times Y is equal to 0. Okay, so it basically preserves dot products. This follows, 4 follows from 3. All right, so let me give you an example of an orthonormal orthogonal matrix. So this actually is the same one that we did before. So we already checked the inner products. So 1 over the square root of 6 minus 2 over the square root of 6, 1 over the square root of 6, 0, 1 over the square root of 5, 2 over the square root of 5, minus 5 over the square root of 30, minus 2 over the square root of 30, and 1 over the square root of 30. Okay, so we actually showed before a while back that this set over here is actually an orthonormal set. So all I'm going to do, all I did was I put that set or those vectors down the columns of this matrix over here. Okay, so I put them down the columns of the matrix, and you could check that this is an orthonormal matrix. Of course, it is an orthogonal matrix. All right, any questions on this so far? No. All right. Now, another reason why we like orthogonal or orthonormal bases, or even orthogonal bases, is that projections are really nice with respect to orthogonal bases. So I want to talk about what's called the orthogonal decomposition theorem. Okay. All right. So here's the idea. So remember we had this idea of projection. So let me just write it this way. So let's do the one-dimensional case. So here's y, and then I had a vector down here. Let's see. I don't know what we call it. Well, let me just put it this way. Sorry. I didn't draw the picture correctly, so let me redraw the picture a little bit. All right. So let me redraw the picture. So let me draw bigger too, so it's more clear. Okay, so here's a vector y. Okay. And then we take a line which sort of looks like this. So let's just say I take a line, call it L. Okay. So last time what we did was we actually saw how to write a projection. So we actually can decompose y in terms of a vector on the line L and a vector which is perpendicular to y. So we had this projection y hat, okay, and we also had this vector z, which goes in this direction here. So we decomposed y in terms of y hat plus z. And given a vector on that line, we can actually find what y hat was. Okay, so suppose that L is a span of this vector, I'll call it x. Okay? So then y hat was going to be y dot x over what? X dot x, right? Times the vector x. Okay, so we had this formula for the projection like this. All right, so now what we'd like to do is we'd like to extend this to more than one dimension. So this is the one-dimensional picture. Okay, so instead of a line, let's take a plane. All right, so I'll draw the plane, and let's draw it in action green. Okay, so here's a plane over here like this. So let's call that W. Okay. So similarly, I want to take a vector y and I want to actually write it in terms of the vector in the plane and something orthogonal to the plane. Okay, so here's a multi-dimensional picture. So I take this vector y out here, okay, and basically I want to do the same thing. I want to write it in terms of a component inside the plane, and then I want to write it with z being perpendicular. So we want, the idea is y to be equal to y hat plus z, where y hat is in W and z is in the orthogonal complement. So it's perpendicular to W. Okay, does this make sense? So this is the multi-dimensional picture. So this is the multi-dimensional picture. Okay. Any questions so far on this? All right, so I need to give you more information to do this. And it turns out that that y hat is easy to write in terms of inner products if I have a orthogonal basis for W. Okay. So let me remark, we can write y hat in terms of inner products or dot products as long as we have an orthogonal basis for W. Okay, so that's what the orthogonal decomposition theorem is going to say. All right, so now that I've set you up with a picture, I'm hoping that this theorem is going to make sense. So this is called the orthogonal decomposition theorem. Okay. All right. So the theorem says the following. So let W be a subspace of Ra. Okay, so W looks like the plane I have up here. Okay. So every Y in Rn can be expressed as Y equals Y hat plus Z, where Y hat is in W and Z is perpendicular to W. Okay. And this decomposition is unique. Okay. Now, if we have an orthonormal or orthogonal basis for W, so moreover, if U1, U2 up to UT is an orthogonal basis for W, then Y hat has a nice form. Just Y dot U1 over U1 dot U1 times U1 plus Y dot U2 over U2 dot U2 of U2. Okay. So these are all vectors. I'm going to sometimes suppress them if it gets to be too much. So Y dot UT over UT dot UT dot the vector UT. So once you have Y hat, you can find Z pretty easily by just subtracting off. So Z is just Y minus Y hat. Okay. So this bottom line generalizes the projection formula for one dimension over here. So in order to generalize the formula, you need an orthogonal basis to write everything in terms of dot products. Okay. All right. So one question you may ask is, why does every subspace have an orthogonal basis? And it turns out that that's a true statement, but we'll prove that later on. So you sort of have to take it on faith that if I give you a subspace like a plane or line or a three space, for example, you can actually find a basis which is orthogonal. Okay. So let me just write that as a fact. So fact is that every subspace of Rn has an orthogonal basis. And we'll actually prove this using Gram-Schmidt. So we're going to prove this by what's called the Gram-Schmidt, which we'll probably discuss on Monday, orthogonalization process. A lot of words. Okay. All right, so let's actually prove this. So the statement is longer than the actual verification. So prove. Okay. So consider Y hat Okay. So consider y hat as in star. Okay. So let's assume that we just write this y hat in this way. We're given y, we just write out y hat in this way. So then clearly, y hat is in the span of W. So this is actually in W, because it's in the span of the U1 of the U2s. Okay. And let's say I take Z dot Uj, and let's show that the dot product is equal to 0. So Z is going to be equal to y minus y hat by definition, dot Uj. Well, when I take y dot Uj, what do I get? Well, I'm only going to pick out the component involving Uj, right? So I get y dot Uj, Uj dot Uj times Uj dot Uj. Okay, that's the one for y hat. And then y is just going to be y dot Uj. So actually, let me just erase here. Yeah, messed up. Okay, let me just try it again. Okay, so this is going to be equal to y dot Uj minus, okay, so when I take y hat dot Uj, I just use the formula above, and then this is what I get. And so notice that this cancels with that, so indeed I get 0. So that means that Z is orthogonal to Uj for all j, and that means that Z is in the perpendicular, the orthogonal complement. Okay, so given an orthogonal basis, I can decompose y. So y is equal to y hat plus z. Okay, so this part's okay as long as I have an orthogonal basis, because I have a formula for y hat. Okay, so let's show uniqueness. So this shows existence, that you can actually do it. And now let's prove uniqueness. All right, so suppose that y is equal to y hat plus z, and it's also equal to, let's say y1 plus z1, okay, and y2 hat plus z2. Okay, so we've decomposed y in two different ways, where y1 and y2 are in W, and z1 and z2 are perpendicular to W. Okay. So this means that that y1 hat minus y2 hat is going to be equal to z2 minus z1. Okay, so both of these are subspaces. So this side is in W, this side is in W perp, because they're both subspaces. All right. But what do we know about the intersection with W and W perp? What's that going to be equal to? Okay, it'll be 0, right? Okay, so 0. So this implies that y1 hat has to be equal to y2 hat, and z2 has to be equal to z1. Okay, so that proves the uniqueness. So we're done. Okay, any questions on this? So whenever we have a subspace, orthogonal basis, we can always take any vector in Rn and decompose it in terms of linear combination of those, orthogonal vectors and something which is perpendicular. So again, this is the picture you should be thinking about. Okay, so to finish off the class for today, let's do an example. Okay. So it's all computation. Okay. So let U1 equal 0, 1, minus 4, 1. Okay. U2 to be equal to 3, 5, 1, minus 1. And U3 to be equal to 1, 0, 1, 4. Okay. All right. So first of all, and let W to be the span of U1, U2, and U3. Okay. So first of all, let's actually check whether this is an orthonormal or orthogonal set. So if I take U1 dot U2, what do I get? Is dot product 0 or not? Good. U1 and U3.
0.
Okay. U2 and U3. 3 plus 1, 0. Okay. So therefore, so you just check U1, U2, and U3 are an orthogonal basis for W. Okay, so we have an orthogonal basis for W. All right, now what I'm going to do is I'm going to take a vector and I'll write it in terms of y hat plus z. So consider y, let's see, let's call it 10, minus 8, 2, and 0. So what we're going to do is we're going to write y equals y hat plus z, where y hat is in W and z is in the orthogonal complement. And we know this decomposition to. Right? Okay, so what we have to do is we have to take dot products, right? So let's just do that right now. So when I take U1 dot y, what do I get? Negative 16. Okay, good. Let's say I take U2 dot y, what do I get? That sounds right, because it's 30 minus 40 plus 2. Okay, negative 8. Okay. U3 dot y. What do we get?
12.
Okay, U3, you're faster than. Let's see, 3 plus 1 plus, oops, sorry, I'm looking, sorry, 10 plus 2, that's right. 10 plus 2, that's 12. Good, good. All right, so that gives you the first ones. Okay. U1 dot U1. What's that equal to? Okay, so 1 squared, that's right. Okay. U2 dot U2. Yeah, that looks right. So let's say it's,
25 plus 9 plus 2.
yeah, 25 plus 9, 34, 36, right? Is that what you want? Okay, and U3 dot U3.
7. No. 18.
18.
18.
All right, good. Everyone kind of get this? All right, so we take a bunch of dot products, and now U hat, y hat, sorry, is equal to minus 16 over 18 times U1. Okay, so let me see if I can keep this on the screen here. 0, 1, minus 4, 1. Okay? And then I take U2 dot Y over U2, U2. That's that. Oh, that was nasty. Let's see. Okay, so this is going to be what? Minus 8 over 16? 36, sorry. Times. Okay, so I need to figure out what this other one was. 351 minus 1. Okay. And then finally, I take 12 over 18, and then I take this one up here, 1014. Okay, so let's see. Let's get rid of that. Okay, does everyone understand how we got that? All right. Now, how do I find Z?
Is the vector y minus y.
Okay, good. So Z is equal to Y minus Y hat. Okay, so you know what Y is, so it's just, I won't write the whole thing out. So Y is 10 minus 8 to 0 minus Y hat, and Y hat is this stuff over here. Okay, and then you can go and you can simplify. Make everything nice and neat if you want. Okay, any questions on this? All right, so let me say why this is important. So why is this important? Well, when you think about it, what you'd like is, if you have a vector y out here, and you sit outside someplace, you have a subspace W down over here. You actually want to find the point on W which is closest to y. So let's say y hat, and this is the z here. So y hat is the point on W closest, we'll make that precise, to y. All right. So, you know, in applications, think about, like, you know, you have a bunch of data, which is given on the span of W. And then you have something which is kind of an outward. And so what you want is you want to actually find something which is close in approximation to that outlier. And so this gives us a method to do this in order to find the point which is actually closest to this point one outside. And this will be sort of the idea of these squares. All right, so let me stop. Do we have any questions from the Zoom audience? From the regular audience? Okay, so we'll stop here, and I wish everyone a happy weekend.
Thank you.